Hi everyone, this week's tutorial is based on tutorial problems 11. The tutorial questions have already been uploaded on your Moodle, right? I hope you guys have at least gone over it and tried attempting them. There are 5 tutorial questions for this week's tutorial, and the tutorials are based on root locus, right? So let's start with question number 1. Question number 1 says that question number 1 is to plot the root locus pattern of the system whose forward path transfer function is g of s is equal to 200 upon s plus 20. So the first step is to identify the poles and the zeros. So if we identify the poles and the zeros, so looking at the numerator there is no zeros, looking at the denominator there is one pole. So if we plot the pole on the imaginary and the real axis, right, so the pole will fall somewhere over here. Then what we need to do, follow the first 5 basic rules, right? The first 5 basic rules is to identify the number of branches. So number of branches is equal to the number of closed loop poles, which is also equal to the number of open loop poles. So there is only one pole over here, so there will be one branch, right? So there will be one branch. Number 2, it is symmetry about the real axis, right? Number 3 is rule number 3 is the real axis segments, right? So just looking at the real axis segment rule, it says that on the real axis the segment exists on the left hand side of the odd numbered 0 pole, right? So basically what you need to do, like in this rule it states that you need to tabulate your poles and zeros, right, in a descending order. So basically going from right to left of a real axis, right? So order it, right? So if your pole comes first, your pole will be there, then your zero, and then maybe your pole, and then again another pole, and then zero. So basically just tabulate it in descending order as per its value, right? So over here we have just got one pole, so that's your point number 1. So that's your, what do you say, that's your odd numbered pole, right? So your odd numbered pole you have, so it will exist on the left hand side of it. So we know it will be existing on the left hand side of it, right? And then going on to the 4th point, that is starting and the ending point. So the starting and the ending point rule states that the root locus will start from a pole and end at a 0, right? So now you know that this is a pole, so it will start from this point and it will end at a 0, so, right? It can be a finite or infinite 0. So that means the arrowhead will be pointing something like this, right? So you basically get this much sketch, and the last point states the behavior at infinity. So basically if you get this, your behavior at infinity is, let's say, it will also go towards infinite, right? So you'll be getting a root locus plot for this particular transfer function as something like this, right? In this point 1 and this point 1, it falls on the root locus, right? Basically it's falling, it is on the root locus pattern of this particular transfer function. So we say that it falls on the root locus, right? Moving on to the second question, right? The second question is to plot the root locus pattern of a system whose forward path transfer function is g of s is equal to k upon s plus 3 and s plus 4, right? So again what we need to do is to identify the poles and the zeros, right? So there is no zeros, there's 2 poles, -3 and -4, right? So we have when we plot the zeros and the poles on the imaginary against the real axis, right? So there is no zeros, there's 2 poles, -3 and -4. If we plot that, so we'll be getting 2 poles, -3 and -4. Remember, we are using a x for a pole and 0 for a 0, right? Or I mean an O or open circle for your zeros, right? So if we get something like this, right, then we go over the basic rules. So the number of branches, so So how many branches will be having? It is equal to the number of poles. So there's 2 poles, so that means there will be 2 branches, right? So there will be 2 branches, and it will be symmetry about the real axis, right? So we know that. Then moving on to the third rule, that is real axis segment, right? So the segment will exist on the left hand side of the odd number 0 or pole, right? So this is your point 1, right, going from right to left. So this is your first point, so this is your odd numbered 1, and this is your point number 2, this is odd numbered point 2, right? So it will exist on the left hand side of a odd number 0 or pole. So that what that means is the segment will be existing over here, right? So we know that, right? Now moving on to the fourth rule, which is starting in the ending point. So it will start from a pole and it is 0, right? So we know that, right? So the arrowhead will be going like this, right? Since both are poles, right? Now behavior at infinity, right? So what we need to do is to identify the asymptotes, right? Behavior at infinity, we need to identify the asymptotes. So just from this, we know that the 2 arrowheads are colliding, right? So what that means, there's a pole, so it has to end at a 0, right? So since there is no 0, it will have a infinite 0. So there will be a breakout points from here, right? Breakaway points, right? Breakaway points from the center of here, somewhere here. So first thing is to identify the breakaway points, right? To do that, what we need to do, we take this transfer function and equate it to -1, right? So basically take this, equate it to -1, right? So if we do that, if we do this, right? So that means if we expand this, we get k upon s squared plus 7s plus 1, and then we equate it to -1, because for a root locus to exist, it has to follow this criteria, right? K times g of s, h of s is equal to -1. Now what we need to do is make k the subject of the formula. If we make that k the subject of the formula, we get k is equal to negative of the denominator, that is negative s squared minus 7s minus 12, right? Now what we need to do is to differentiate this k. If we do that, we get negative 2s minus 7, right? So we get negative 2s minus 7. Now what we need to do is to equate, after differentiating, we need to equate it to 0. So we'll be getting, it won't be 2s plus 7, right? It will be negative 2s minus 7, right? Then we equate it to 0 and solve for s. So if we do that, we get s is equal to negative 3.5, right? So that means at s is equal to negative 3.5, there will be a breakaway point. So at negative 3.5, the point is over here, right? So that will be a breakaway point. Now what we need to do is to identify the behavior at the infinity, which is to basically identify the asymptotes, right? So we already know the breakaway point is at this point, so we don't have to find the intersection of the asymptote or something like that. So we just need to identify the angle, right? The asymptote angle. So the asymptote angle is given by 2k plus 1, right? 2k plus 1 times 180 upon number of poles minus number of zeros, right? So when k is equal to 0, right? So 2k, right? The formula is to identify the angle, right? The asymptote angle is equal to 2k plus 1, right, into 180 degrees, right, upon number of poles, right? Number of poles minus number of zeros. So let's put a number sign over here. right? So when k is equal to 0 and your pole number of poles over here is 2 poles, 0 is 0, so 2 minus 0, and when your k value is 0, right, so this part will be 0, so it will be just 1 multiplied by 180 upon 2 minus 0, which is equal to positive negative 90 degrees, right? Yes, and the asymptote, the angle for asymptote number 2 is given by when k is equal to 1, right? Substituting k is equal to 1 into this formula, we get positive negative 270 degrees, right? So when we plot this, right, these asymptotes over here, so we know that the break-in breakout points are at this particular point at negative 3.5, so that is the point negative 3.5, and the asymptotes are at positive negative 90 degrees, right? So there is an asymptote, so basically positive negative 90 degrees, so there will be a breakout point, and it will be, the arrows will be pointing up and down. So basically the root locus pattern for this particular transfer function is given by this, right? So this is your root locus pattern for this particular transfer function. Now let's move on to question number 3. Question number 3 is to plot the root locus pattern of the system whose forward part transfer function is g of s is equal to k upon s into s plus 2 into s plus 3, right? So again, what you need to do is to list down your poles and the zeros, right? So looking at the numerator, there is no zeros. Looking at the denominator, there is one pole at 0, one at negative 2, and one at negative 3, right? So we need to plot our zeros and the poles on the real and the imaginary axis, right? So if you do that, there is no zeros, only poles, right? So one pole will be at 0, one pole will be at negative 2, and one pole will be at negative 3, right? So now following the 5 basic rules for sketching the root locus, right? The five important one, right? The first 5, let's look at that. Number of branches, there will be number of branches. How many branches will be there? 1, 2, and 3, right? So number of branches is equal to number of poles, right? So there will be 3 branches. It will be symmetry about the real axis. The number of real axis segment, again what you need to do is to basically list down your poles and zeros, right? So basically basically what you can say is taking points one by one, right, numbering them when you go from right to left on your real axis, right? So your branches will exist on the odd number, on the left hand side of the odd number points, right? So if you label this point, right, this will be your first point, right, when you are going from right to left. So point number 1, point number 2, and point number 3, right? So the segments will be existing on the right hand side, on the left hand side of the odd number points. So there will be a segment over here, right? There will be a segment over here, right? There will be a segment over on point number 3 as well, right? Set. Now going to point number 4, that is labeling your starting and the ending point. So you know the starting point will be a finite or infinite pole, and the ending point will be a finite or an infinite 0, right? So since all of them are poles, so that will be the point it will be going out, right? So these are the starting points, right? So this is again a pole, so that is the starting point. So this is a pole, so it will be going out, right? So it will be a starting point again. So that's how you get, right? Now looking at this segment, right? This segment is okay. This segment has no issues. So basically the root locus will be something like this for this particular point, right, onwards. So there will be a breakout point, right, since both of them are poles, right? So there has to be a breakout point, right, so that it will be going to a infinite 0, right? Since there is no zeros for this system, so there has to be a infinite 0. So what we do is to identify the breakaway points, right, over here. To do that, what we need to do is again go back, follow this rule, right? Follow this rule. For a point to be on the root locus, it has to follow this rule, right? So basically what we need to do is to equate this function, right? This equal to -1, right? And then solve for k. So basically what happens is that if we solve for this, that means k is equal to negative denominator, right? So if we solve for that, let's say this part is equal to a, right? So k is equal to, if we take this 8 multiply it to -1, you'll get negative a, right? Right? A is equal to this denominator, right? So now what we need to do is to differentiate k, right, and equate it to 0. So we'll be getting the minimum output, right? So basically it will give us the breakaway and the break-in point, right? So a breakaway point occurs when the gain is maximum, and a break-in point happens when the gain is minimum, right? So what happens is, now what we do is, and we basically follow that and identify the breakaway point, right? So by doing that, right, by solving for k, right, so k is basically the negative of this denominator, right, and then differentiating, right, in terms of s and equating it to 0, right? So if we differentiate the denominator, right, so we'll be getting 3s squared plus 10s plus 6, right? So that's what we get. So this whole thing has to be multiplied by -1. So why we forget about this -1? Because this is a -1. If we take it to the other side, so basically 0 divided by -1 is again equal to 0. So we forget about that negative, right? So we usually forget about that negative and solve for the differentiated denominator, right? So even if you take that negative, right, if you take that negative, so basically if you solve for -3s squared minus 10s minus 6 is equal to 0, you'll be still getting these two solutions, right? So s is equal to -0.784 and s is equal to -2.549. So when s is equal to this particular 2 points, so your k is either maximum or minimum, right? So just looking at this root locus, right, you know that this point will be on the root locus, right, on the root locus pattern, right, this point. However, this point does not, like, -2.549 will be somewhere here, right? So it does not fall on this segment, right? So basically you can ignore this point, right? Later on you won't be using this point, right? We'll be just using this one because this one falls on the root locus, right? Now you know your breakaway point, right? Now what we need to do is to identify the asymptote, right? The asymptote and the intersection of the asymptote, right? So what we do is to find the asymptote angle, right? To identify the asymptote angle, we use this formula, right? 2k plus 1 into 180 degrees holding upon number of poles minus number of zeros, right? So when k is equal to 0, that is 180 upon number of zeros, number of poles minus number of zeros, right? Number of poles are 3, number of zeros are 0, so you get 3, right? So 180 upon 3, you get positive -60 degrees, and when k is equal to 1, so basically 3 times 180 degrees, right? So if you substitute 1 in place over here, so 2 times 1 plus 1 is 3, right? So 3 times 180 whole thing upon 3, right, which is equal to positive -180 degrees, right? Now the intersection of the asymptote, right? The intersection of the asymptote is given by the sum of poles minus the sum of zeros holding upon number of poles minus number of zeros, right? So which is equal to, so sum of poles, that is 0 plus -2 plus -3, right, minus sum of zeros, so sum of zeros is equal to 0, so we just minus 0 holding upon number of poles minus number of zeros, that is 3. minus 0, right? So you get negative 1.667, right? So that is your intersection for your asymptote, right? Now we also need to identify the, so since there's an asymptote, right, it will be at an angle of positive negative 60 degrees or positive negative 180 degrees. So either way it can intersect the j omega axis, right? So we just need to check for the intersection. If the asymptote, uh, if the graph intersects, right, the root locus pattern intersects the j omega axis, right? So if we do that, what we need to do is to basically, in place of s, substitute j omega and right and manipulate this equation into the rectangular form, that is a plus jb, right? So in that particular form, right? So basically real plus or minus plus minus the imaginary part, right? So manipulating that, we get something like this, right? Now what we need to do, if we need to find the intersection, the j omega axis intersection, we need to equate the real value to 0, right? So that means this particular value, the real value, to 0, and solve for omega, right? So if we solve for omega, we get omega is equal to plus minus 2.5, right? Now what we need to do is take this plus minus 2.5 and just substitute it into this formula, right? So you'll be getting your intersection, right? So basically you'll be getting omega is equal to 2.5. Now plotting all this, so you know the segments, right? So there was one segment over here, right, between 0 and negative 2, one segment between negative 3, negative 3 and negative infinity, right? So this portion is fine, like I said earlier on, right? Now there was a breakout point, right, between this 0 and negative 2. So there's a breakout point at negative 0.78, right, which we calculated over here. Negative 2.549 is outside the segment, right? So it does not fall on the root locus, right? So we avoid that. So negative 0.78, that's the point where the breakaway happens, right? Now we need to draw the asymptotes. The asymptotes are, the intersection of the asymptote is at negative 1.667, right? Negative 1.667 is slightly close to negative 2, right? So it will be somewhere over here at an angle of positive negative 60 degrees, right? So positive negative 60 degrees, right? If we draw that, and the asymptote, the other asymptote angle was positive negative 180 degrees. So the other angle was this one. So it is basically following the real axis, so we avoid this one, right? Positive negative 180 degrees can be avoided, so we just take this one, right? Positive negative 180, positive negative 60 degrees, and draw the asymptote. So it will be, the asymptote will be intersecting at negative 1.667 at an angle of positive negative 60 degrees, right? So the asymptotes will be like going like this, right? So you know the j omega axis will be intersecting at positive negative, the root locus pattern will be intersecting at positive negative 2.5, right? So positive negative 2.5 is somewhere here, so it breaks away at negative 0.78, right? Breaks away at negative 0.78 and intersects at omega is equal to 2.5. So there will be an arrowhead like this, right? So it will be an arrowhead over here. Likewise, it is symmetry about the real axis, so the pattern will be something like this, right? And your asymptote, you make sure it does not touch the asymptote. It is closely following the asymptote, right? So your root locus pattern for this particular equation is, for transfer function, right, is something like this, right? So moving on to the question number 4. Question number 4 is to plot the root locus pattern of the system whose forward path transfer function is g of s is equal to k into s plus 1 upon s into s plus 2 into s squared plus 2s plus 5, right? Again, you need to identify the zeros and the poles, right? So your zeros is equal to negative 1, right? You can, from here you can just see that your zeros, right? zeros are equal to -1, right? So there's only one zero. Your poles are equal to 0, -2, and solving for this, right? Equating this particular portion and solving to 0, right? Your your poles are equal to -1, negative j2, right? And -1 plus j2, right? So listing your poles, right? So -2, right? The poles for this one, -1 minus j2, -1 plus j2, and 0, right? Now what we need to do is to plot the zeros and the poles on the imaginary and the real axis, right? Over here. So if you plot that, there's one pole at 0, then there's one pole at there's 1 0 at -1, right? -1, and then there's there's two values, right? That's a complex number values for the poles, right? Plot that, right? Plot that, right? So if you plot this, you'll be getting the poles and the zeros of something like this, right? Again, the number of branches is equal to the number of poles. So there's how many poles? 1, 2, 3, 4. So there's 4 poles, so that means there will be 4 branches. It will be symmetry about the real axis. It will be how many real axis segments will be there. So if we level the points, so there will be one segment existing between one segment existing between 0 and -1, right? And the other segment, right, going from right to left, right? There will be one segment existing over here, and this will be your point 1, this is your point 2, and this is your point 3. So it will be existing on the left hand side of the odd numbered points, right? So there's one, right, one segment over here, and left of point number 3 as well, right? So point number 1, point number 2, and point number 3, right? So there you go. Then you have to label the starting and the ending point. The starting point is from a pole to 0, right? So the arrow will be going something like this, right? Now what we need to do is to identify the behavior at infinity, right? So this portion is okay, this portion is fine, totally fine. What we need to do is there won't be a breakaway point, right? So there's no need to identify the breakaway or break-in point, right? But there will be an angle of departure, right? Since it's a pole, so there will be an angle of departure. That's what we need to identify over here. And so if it has a angle of departure, it will also have a asymptote, right? So we need to identify the asymptotes as well. Angle of departure, the asymptotes, and the j omega crossover, right? J omega axis crossover. So what we do is to identify the asymptote, right? We can start with the asymptote angles. Asymptote angles are given by 2k plus 1 into 180 holding upon number of poles minus number of zeros. So again, when k is equal to 0, right, so it will be plus minus 180 degrees upon, so there's 4 poles minus 1 0, 4 minus 1, you get plus minus 60 degrees, right? When k is equal to 2, you get plus minus 180 degrees. When k is equal to 3, you get plus minus 5 times 180 degrees upon 3, which is equal to plus minus 300 degrees, right? And then what we need to do is to identify the asymptote intersection, right? So to identify the asymptote intercept, it is given by the formula of sum of poles minus sum of zeros holding upon number of poles minus number of zeros. So directly substituting the values, the sum of the poles, right, minus the sum of the zeros holding upon 4 minus 1, you get 1, right? So the intercept happens, I mean the asymptote intercept happens at -1, right? Then what we need to also identify, we know the asymptote angle and the asymptote, right? We have solved for the asymptote, right? The angle and the intercept. We need to identify the intercept, right? The root locus intercept at the j omega axis, right? So again, what we need to do is to substitute j omega in place of s, right? And then manipulate the equation so that you have a rectangular form in form of real value plus minus imaginary value, right? So when we do that, we manipulate and solve for the real part is equal to 0. We get omega is equal to, sorry, this has to be real value, right? We have to solve for real value, right? Real is equal to 0. So we get omega is equal to plus minus 2.56 right per second, right? So that will be your j omega intercept, right? J omega intercept. Now what we need to do is to, since it's a pole, so it will be going outwards, right? It will be going outwards. So what we need to do is to identify the angle of departure, not the angle of arrival. So to find the angle of departure, what we do is to find the, so taking this point we calculate the angle of departure, right? So to calculate the angle of departure, all the sum of these angles will be equal to 180 degrees or negative 180 degrees, either way, whatever you take it, right? So all the angles relative to a pole, or all the angles of a pole will be negative, and all the angles of a zeros will be positive. So if we calculate the angle for this particular departure, right, the angle of departure over here, that if we take it as x, then we take all the angles relative to this particular point, right? So this will be your angle of theta, yeah, theta 1. This will be 90 degrees, right? This is theta 2. This will further extend down. This is again 90 degrees, right? This is theta 3, and this is another angle. This is theta 4. So now if you calculate theta 1 is equal to, it's 90 degrees plus tangent inverse of half, right? So this is 90 degrees, and then this is, if you find this angle, this is tangent theta of tangent theta is equal to opposite, which is 1, and adjacent is 2. So it is 1 upon 2. Tangent theta is equal to 1 upon 2. So theta over here, this theta is equal to this particular theta, right? This particular theta is equal to tangent inverse of half, right? So that's how you get theta 1, this whole theta, right? This is 90 degrees, and then this theta. Theta 2 is 90 degrees itself, right? Straight coming down, right, at -1. This is again straight going down to at -2, right, or -1. So this is again 90 degrees. So you have to just find theta 4. Theta 4 is equal to, right, again you can use the tangent rule. So it will be tangent inverse of opposite is 2, right, and adjacent is 1. There's a small triangle, right? This is the triangle that you can form. That's how you get theta 4. The sum of all the angles is equal to 180 degrees or minus 180 degrees. I'll be using 180 degrees, right? So 180 degrees and minus 180 degrees are same, right? So I'll be taking that. So all the angles, right, of a pole are equal to negative value, and all the angles of a zero is positive angle. So theta 1 is equal to, this whole thing will be equal to 116.57. so you'll be taking minus 116.57, right? Then theta 2 is again it is 0, right? So you'll be taking positive 90 degrees, then this is minus 90 degrees, right? And then this is again of a pole, so it will be minus. So minus this angle A is equal to 63.43 degrees, right? So which is equal to, oh, here I've forgotten about this angle of departure that we are calculating. It is of a pole, so it will be minus x, right? Which is equal to 180 degrees. So if you solve for x, you'll be getting minus 360 degrees, right? So minus 360 degrees is same as 0 degrees, right? So angle of departure is equal to 0 degrees for this particular pole, right, over here. And you know that the root locus is symmetry about the real axis, right? So the same will be for this angle of departure. If you reflect it, right, reflect this angle of departure across this real axis, the angle of departure over here will be 0 as well, right? So that means it will be closely following by, and then it will start to follow the asymptote, right? So now what we can do, if we have found all the points, now we need to plot this, right? So if we plot this, and if we plot that, we'll be getting a plot of something like this. So you know there is a pole at -2, there's a pole at -1 plus 2j, there's a pole at -1 minus 2j, and a pole at 0, and there is one 0 at -1, right? So there is also the intercept of the asymptote is also at -1, right? So the asymptote will be at -1 at an angle of positive -60 degrees, right? So at an angle of positive -60 degrees, right? So this is 60 degrees, positive 60 degrees, this is -60 degrees, right? And the angle of departure over here is 0, right? So 2j and 2.56j is not really far. Over here we have shown it really far, but it will be really close. So it will be really close, so it will go, and then as soon as it starts to arrive at its asymptote, it will start to fall. So it will be something like this, right? The graph intercepts at positive -2.56, right? The asymptote doesn't intercept at that. So your root locus is something like this, right? Now moving on to the next question, right? The open loop transfer function of a unity feedback control system is given by g of s is equal to k into s plus 1 holding upon s squared, right? We have to sketch the root locus plot for the system by determining the number, angle, and the centroid of the asymptotes, angle of departure of the root loci from the poles, the breakpoints, right? So just from this, we identify the poles and the zeros. So over here there is 1 0 at -1, and there's 2 poles at 0, right? So two poles at 0, and 2 poles at 0, right? And 1 0 at -1, right? So that'll be our second. So from these, point A will not lie on the root locus, while point B will lie on the root locus, right? So to find the asymptote, right, we need to find the asymptote, the centroid, the angle, right? So to find the asymptote angle, that is 2k plus 1 into 180 degrees upon p minus z, right? Where k is equal to 0, 1, 2, 3, whatever, right? You can take k is equal to plus minus as well, right? Plus minus 1, plus minus 2, plus minus 3, right? So finding the angle of the asymptote, that is 2k plus 1 into 180 degrees upon number of poles minus number of zeros, right? So that be, when taking k is equal to 0, that would be 2 times 0 plus 1 holding upon 2 minus 1 times 180 degrees. So that would be 180 upon 180 times 1, which is equal to 180, right? So that will be your angle of the asymptote. Your centroid, right? The centroid is given by the real axis intercept of the asymptote, right, which is equal to sum of finite poles minus sum of finite zeros divided by number of poles minus number of zeros, right? So that would be you have two poles, right, 0 plus 0, right, sum of that would be 0, minus you have 1 0 at minus 1, so minus 1, right, holding upon 2 minus 1, right, you have two poles and 1 0, right, so that will be equal to 1, so your centroid will be equal to 1. To find your breakaway points, right, to find the breakaway point, again you have to follow this rule. Whatever that is given, that will be an open loop, right, that will be k times g of s, h of s is equal to -1, right. Basically what you need to do is over here you need to equate these, right. If you equate these, you just need to equate these, right, k upon s plus 1 whole thing upon s squared is equal to -1, right. Make k the subject of the formula, right, and differentiate. So once you do that, you'll be getting s into s plus 2, right, and then to find the breakaway point you have to equate it to 0, right, so that will give you minimum or maximum, right. So if you do that, you'll have two values for s, right, so either it will be a breakaway or a breaking point, right. So at s is equal to 0 and at s is equal to -2, right. This is what you get when you differentiate k. Now you know there will be two values of k. One is when s is equal to 0 and one at s is equal to -2, right. So these two values, 0 and -2, either it will be a breakaway or a breaking point, right. Then you need to find the angle of departure, right, b, the angle of departure of the root loci from the poles. So from the poles will be 180 degrees -0 -0. This is because all the angles lie on the all of these angles, right, I mean all of the poles, right, and the zeros lie on the real axis, so some of those will be equal to 180 degrees. So basically all of these, right, 180 degrees minus -0 -0 -0 -0, right, all the angles will be 0, so your angle of departure is equal to 180 degrees, right. And then what you need to find is to find the you need to find the breakpoints. We have already found breakpoints, right, so it will be at s is equal to 0 and s is equal to -2. Now we need to plot this, right, sketch this. So if you sketch this, you know there is a breakaway or breaking point at s is equal to 0. So there is a two poles. So what happens is you start from pole, you end at a 0, right. So that means there will be a breakaway point at this particular point. So there will be a breakaway point, and then that will be coming at there will be a breaking point at s is equal to -2. So if you break away from here, then you end up at s is equal to -2, right. And you are starting from a 0, so you are starting from a pole, so you need to end at a 0, right. So 0 is over here, s is equal to -1. So you start, right, so you know your breaking and breakaway point, which is equal to s is equal to 0. You break in at s is equal to -2, right, over here, and then you come to a 0. So you get this, right. You also know that the root locus is symmetric about the real axis, so this side will be something like this. You break away at 0, right, you coming at -2 and you end at 0. So your root locus plot will be something like this. So if you have any other questions regarding this week's tutorial, you can message anyone in the teaching team, right. So that's it for this week's tutorial. Thank you.